Hello everyone and welcome back. I hope you had a great test. Seems quite decent to me. I think FRQ4 was on the easier side. So I'll give my solutions right here, and if I'm wrong anywhere, then please let me know. I'll correct it as soon as possible because I'm not even close to a genius. So let's begin right away. Part A, the functions g and h are given by something and something, and we have to solve for particular values of g of x and h of x. This is a very typical FRQ, so I'll begin right away. So we have g of x is equal to 4, which means I have g of x as 2 times log base 3 of x, and I have a 4 here. So 4 is equal to 2 times log base 3 of x. I simply start by dividing both sides by 2. So I have 2 is equal to log base 3 of x. And from the definition of a logarithm, as I explained earlier, a logarithm essentially means what power do I raise the base number to get the value. So which means what power do I raise 3 to get x? And the answer is 2, which means 3 to the power 2 should be x, which means the value of x is simply 9. In a very similar fashion, we have part 2, where we have h of x is equal to 4 times cosine square of x, and the value is given to us as 3. So 3 is equal to 4 times cosine square of x. Now, whenever you're dealing with trigonometry or logarithms, I will advise you to isolate the x term, the logarithm, or the trigonometry, or the trigonometric part, and get the constant on the one side. So we have, if I divide both sides by 4, I have 3 over 4 to be equal to cosine square x. Now if I take the square root both sides, I have square root of 3 upon square root of 4, which is 2, is equal to cosine x. Now we know that in the interval 0 to pi by 2, cosine is root 3 over 2 at pi over 6. And notice that since they have given the interval 0 to pi by 2, you don't need to mention the other quadrant values for which this satisfies. If you write this much, you will get full credit. So part A was quite easy. Let's move ahead. Part B, we have functions j and k given by something and something, and we have to rewrite j as a single logarithm base 2 without negative exponents in any part of the expression. So again, I'll write it down. We have j of x is equal to log base 2 of x plus 3 times log base 2 of 2. Use the power rule. So we have log base 2 of x plus log base 2 of 2 to the power 3, which means according to the product rule, we have log base 2 times x to the power, times 2 by 3, which gives me log base 2 of 8x. That was very simple and straightforward. Let's move on to the second part. Okay, subpart 2 wants us to write k of x as a single expression in which tangent of x appears only once and no other functions are involved. Now, how would you approach this problem? Well, we already have a tangent of x here, but the problem is this one. So how can you relate cosecant square of x with any tangent function? It could be tan of x or it could be cot of x. So we know from the identities that 1 plus cot square x is cosecant square x, and if I move 1 to the other end, I have cot square x is equal to cosecant square x minus 1, which is exactly what we have. So which means I can replace this expression with this part. So I have my k of x as 6 over tangent of x times cotangent of x square. Now, you should know that cotangent of x is essentially the reciprocal of tan x, right? Cotangent of x is just the reciprocal of tangent of x, which means that cotangent of x square would be this expression square. So now I can replace this guy with this one. So I now have 6 over tangent of x. You take the reciprocal, so I have times tangent square x. Now we have everything in tangent. I simply cut them off. So I cut this here, I cut this, I get a power 1 here. So I now have 6 times tangent of x, which should be your answer because we have followed all the rules. Let's move on to the final part. Okay, part C. The function m is given by m of x is equal to e to the power 2x minus e to the power x minus 12. Find all input values in the domain of m that yield an output value of 0. Okay, so we'll set the function 0 is equal to e to the power 2x minus e to the power x minus 12. Now, compared to the other two, this is slightly tricky, but it's not hard at all. So if I let e to the power x to be equal to, let's say, some value k. Now, it's not necessary for you to make the substitution. You could have directly found out the roots, but I'll take the substitution because it makes it much more easier. So we now have 0 is equal to k square minus k minus 12. Now I'll factor it. I could either use a quadratic formula or I'll recommend that you use splitting the middle term. So I have k squared minus 4k plus 3k minus 12, which gives me k into k minus 4 plus 3 times k minus 4, which means I'll now have k plus 3 times k minus 4, which means that my k could be 4 or negative 3. Now since k was e to the power x, I have e to the power x, which could be equal to negative 3, or I have e to the power x, which could be positive 4. Now look, the domain of e to the power x is positive, right? Whenever you raise e to the power anything, if it's a negative x, we'll have a larger or smaller input. But e to the power x is essentially greater than 0, which means that this is not in the domain. So we'll cancel that out. This is not in the domain. And for this one, it is in the domain. I'll simply take the natural logarithm of both ends. So I have x is equal to ln of 4. And there you go. That's it. Here is your final answer. I hope the solutions were very clear. Again, let me know if I have anything to correct. And see you again. Bye.